Hey there, and welcome. Today we are tackling one of the biggest, most fundamental questions in all of science. We're going to talk about the invisible forces that literally build everything around us, from the food we eat to the phone in your hand. So let's explore that huge question.
No, really think about it for a second. What's stopping everything? You, me, this screen from just poof, dissolving into a cloud of atomic dust? The answer is chemical bonds. It's the ultimate story of attraction, of atoms giving, taking, and sharing to create the incredible, complex world we see.
So here's our game plan. First, we'll get to the bottom of why atoms bother to stick together at all. Then we'll meet the dramatic givers and takers in ionic bonds, the great collaborators in covalent bonds, and then a really interesting special case called the coordinate bond. And finally, we'll tie it all together and see why these different bond types are just so important.
All right, let's jump right in with the big why. At the very heart of all this chemistry, all this bonding, is one single driving force that pretty much every atom shares. It's a deep, deep quest for stability.
So what is a chemical bond, really? Well, it's just that, a force of attraction. It's not a physical link or a tiny string, but it's this powerful, energetic pull that holds atoms together, letting them team up to form all the molecules and compounds that make up our world.
Okay, so what does stability even mean for an atom? It's all about having a full outer shell of electrons. And the best way to think about it is like completing a puzzle. See, an atom with an incomplete shell is kind of antsy. It's unstable, it's reactive. But once it gets that outer shell filled up, now it's stable, it's content, it's chill, kind of like the noble gases. And to get to that happy, stable state, atoms have three main strategies up their sleeves. Three kinds of strong bonds that can form. And we're going to break down every single one, starting with the most dramatic of the bunch. First up, welcome to the world of ionic bonds. Think of this as the high-stakes drama of the atomic world, because it's all about the complete transfer of electrons. We've got our givers, and we've got our takers.
The way it works is actually pretty straightforward. First, you have one atom that just gives away its outermost electrons. We call them valence electrons. Then, another atom swoops in and greedily takes those electrons to finish its own outer shell. This whole transaction creates charged particles called ions. One becomes positive, the other negative. And you know what they say about opposites? They attract. That powerful electrostatic attraction is the ionic bond.
But wait, this can't just happen between any old atoms. You need the perfect setup. You need one atom that isn't holding on to its electrons too tightly. It's got low ionization energy. And you need another atom that desperately wants an electron. It's got high electron affinity. This huge difference in how much they want electrons, their electronegativity, that's the magic ingredient.
And the classic example, the one we all know, is table salt, sodium chloride. Sodium has this one lonely electron in its outer shell that it would just love to get rid of. Chlorine, on the other hand, is just one electron away from a perfect set. So sodium donates, becoming a positive ion. Chlorine accepts, becoming a negative ion. Boom, they stick together. You've got salt. And yeah, table salt is the poster child for ionic bonds. But here's a fun fact for you. The championship title for the most ionic compound on Earth actually goes to cesium fluoride. Why? Because cesium is the most generous electron giver there is, and fluorine is the absolute greediest electron taker. It's a match made in chemistry heaven.
Okay, so that's what happens when one atom is a bully and the other is an easy target. But what happens when you get two atoms that are more evenly matched? Well, that's where our next type of bond comes in, covalent bonds. This isn't about giving and taking. This is all about teamwork and sharing. And this right here is the absolute key difference. In an ionic bond, that electron packs its bags and moves out completely. But in a covalent bond, the atoms decide to co-own one or more electrons. Those shared electrons then buzz around both atoms, holding the whole thing together like glue. So the big idea here is that these bonds form between atoms that have a pretty similar grip on their electrons. Neither one is strong enough to just rip an electron away from the other, so their best option is to compromise and just share. You see this all the time between non-metal atoms. Now, not all sharing is equal. When two identical atoms get together, like two oxygen atoms, they share the electrons perfectly evenly. It's a fair deal. We call that a non-polar bond. But if one atom is a little more electron hungry, like the oxygen in a water molecule, it tugs those shared electrons a little closer to itself. This creates a polar bond, with one end slightly negative and the other slightly positive. And that tiny little imbalance is a huge deal.
It's literally the reason life as we know it can exist.
And this whole sharing thing can happen at different levels. Atoms can share one pair of electrons in a single bond, two pairs in a double bond, or they can go all in and share three pairs in a super strong triple bond. That's what holds the nitrogen molecules in the air we breathe together, and that bond is incredibly strong.
All right, so we've got the givers and takers, and we've got the team players. But what if you could have a bond where the sharing is, well, totally one-sided? That brings us to our third and kind of unique type of bond, the coordinate bond. So a coordinate bond, sometimes you'll hear it called a dative bond. It looks just like a covalent bond because electrons are being shared. But here's the kicker. One atom, the donor, brings both of the electrons to the party. It shares its pair with an acceptor atom that's short on electrons and needs a pair to become stable.
Okay, let's take a look at this picture because it explains it perfectly. You see that ammonia molecule on the left? The nitrogen in the middle is bonded to 3 hydrogens, right? But look closely. It's got these 2 extra electrons just hanging out, not doing anything. That's a lone pair. Now along comes a hydrogen ion, which has no electrons at all. The nitrogen generously says, "Here, you can share my lone pair," and forms a new bond, creating the ammonium ion you see on the right.
And that is the secret sauce for a coordinate bond, this lone pair. It's a pair of electrons in an atom's outer shell that isn't already tied up in another bond. It's just available. And if the right kind of electron-needy atom comes along, it's ready to form a bond.
Okay, that was a lot of atomic-level detail. Givers, shares, one-sided shares, but who cares, right? Why does any of this matter in our day-to-day lives? Well, it matters because everything about a substance, its properties, what it does, comes down to these bonds. And this table here really pulls it all together. You see, with ionic bonds, because electrons are completely transferred, you get these strong, rigid crystal structures like salt, which can conduct electricity when they're melted. Covalent bonds, based on sharing, create individual molecules like water, and they're usually terrible conductors. And those special coordinate bonds, they're key to forming all sorts of complex ions.
And that, right there, is the single most important thing to remember from all of this. Whether something is hard or soft, whether it dissolves in water, whether it conducts electricity, it all comes back to the type of invisible bonds holding its atoms together. It is the bridge from the tiny world of atoms to the world we can actually see and touch.
So let's just wrap up with this one last thought. We've talked about 3 basic rules of how atoms get together: giving, sharing, and generous one-sided sharing. Just think about that. From just those 3 simple rules, you get the mind-boggling diversity of millions upon millions of chemical compounds that make up everything in the known universe. It's a pretty amazing reminder of the simple elegance that's hiding underneath all of nature's complexity.